Okay, well, welcome to this. This is the final video for chapter 2, and it's fairly technical. If you're not interested in the really technical stuff, you might skip this one and move on to the next chapter. But I wanted to show you these bounds on pi of x that were obtained, or similar ones were obtained by Chebychev back in the 1800s. And so it shows us that, if nothing else, that pi of x is somehow connected with this x on log x, which Gauss had realised, and which we'll prove later on in much more detail. This simply gives us a bound of pi of x between 2/3 of x log x and 1.7, so about 0.67 and about 1.7 multiplied by x log x. Pi of x is in between these two. As I mentioned, Chebychev was able to tighten this left-hand constant from 0.67 to 0.9, and the right-hand constant brought down to 1.1, but you can refine these further. We firstly noticed, we saw in one of the earlier proofs, that we have to go a fair way along before we start to see, before we get the results we want. So we have to check by hand, if you like, or by using Maple, that pi of x is less than 1.7, so this is the right-hand inequality. That's less than that if x is less than 1200. We need 1200. You'll see why that number is important in a moment. So I'm going to attack the right-hand side, and what we're going to do, I'm going to prove this using a sort of version of induction. Now, normally induction, you assume it's true for, say, n-1 and prove it's true for n. This version of induction, we're going to assume that this inequality here is true for all x less or equal to n, and then we're going to prove it's also true for 2n. And then we're going to show that it's also true for 2n plus 1, and then you'll need to think a little bit to see that if you assume something is true for n, and you show it's true for 2n and 2n plus 1, then it's true for all n. So I'm going to now suppose that this right-hand inequality is true for all x less or equal to n, and as usual we're going to play with the binomial coefficients. Now, from that earlier lemma that we had, we can say we know that all the primes between n and 2n are factors of this, and so the product of those must be less or equal to this number. So each one of these primes divides this one. And also we saw that 2n choose n is less than 2 to the 2n. So now there are pi of 2n minus pi of n primes strictly between n and 2n, and each of those is greater than n. And so that means I can simply count the number of primes in here, which is this number, and replacing p with n, I can say that this product is bigger or equal to n to the pi 2n minus pi of n, and it's still less than 2 to the 2n. As usual, we're going to take logarithms to the base n of both sides of this inequality, and to the base n then I get pi of 2n minus pi of n is less or equal to 2n log to the base n of 2, and as usual we convert this from base n to base e. Now 2 log 2 is roughly 1.386, so this is going to be less than 1.39 n on log n. Now, by my assumption, we're assuming that pi of n is less than 1.7 log n, and this is because we've assumed this is the result is true for all x up to some point n. So, rearranging this, we can say pi of n is less than this quantity here, plus pi of n, and then I can replace this with less than 1.7 n on log n, and bring the n on log n's together to get this plus this, which is 3.09. Now, it is an exercise, just fiddling around with inequalities, to show that this number here is less than 1.7 times 2n on log 2n, That is, if n is bigger than 1200. In fact, I did the calculations, it's actually true when n is bigger than 1001. And in fact, you can perhaps convince yourself of that by doing a little calculation using Maple, which I did here. So here again, I've plonked the two functions in, and I've subtracted them, and you can see it goes negative. We had to get up to about a bit less than 1200, but certainly for 1200 beyond, it looks as though this goes negative, so the inequality looks to be true there, and then you can give a proper analytical proof of it. So that's why we needed to go to roughly about 1200, because the inequality then becomes true. So this is going to be less than that, and this is the right-hand side of our desired inequality, except we've now proven it true for 2n. So, hence, if the inequality is true for n, then it's true for 2n. Also, pi of 2n plus 1, the number of primes less or equal to 2n plus 1, is less or equal to the number of primes less than 2n plus possibly one more if 2n plus 1 happen to be prime. And we've just shown that this is less than 3.09 n on log n plus 1. And again, I claim that this is less than that. Again, we can use a Maple picture, a Maple sketch. In fact, I think the one I showed you was the one I wanted here. You can use a Maple sketch here again to show that if n is bigger than 1200, then this less than that is true. So that tells me if the inequality is true for n, then it's true for 2n and 2n plus 1. And then by this version of induction, it holds for all n. You might like to think about that, because if it's true for 1, then it's true for 2 and 3. And if it's true for 2, then it's true for 4 and 5, and so on. If it's true for 3, it's true for 6 and 7, and so on. And you can see that it will be true for all n by an inductive argument. Now, for the left-hand side, well, the left-hand side is, we'll need a slightly different proof. Again, we'll need to be using the Genres Theorem, which we had in the earlier lemma. The highest power of p, which divides n choose k, well, it's going to be the highest power of p that divides n factorial, and then minus the highest power of p that divides these two. And Legendre's symbol then tells us that p to the nu p is given by nu p is the sum of n, that's from the n on the top, divided by p to the r, take the floor, and then minus k from the k in the bottom, and n minus k from the n minus k here. Now, it's a simple exercise to show that the difference of these two floors is less than the floor of the difference plus 1, less or equal to, and that means then if we apply that here, then this minus this is less or equal to n minus k on p to the r plus 1, and that cancels with this one. So each term in the sum is either, it's got to be less than or equal to 1, so it's either 0 or 1. Furthermore, if we take p to the r bigger than n, i.e. if we take r bigger than the log to the base p of n, then each term of the sum is 0. Thus, we need this nu of p is going to have to be less than the log of n to the base p, and hence when I work out p to the nu p, basic log laws get you equals n. That tells me then that the binomial coefficient n over k is going to be the product of all the primes that divide n choose k to their respective prime powers, and my p to the nu p is less than n, and the primes have to be less than n, and so I take all the, not just the primes that divide this, take all the primes less or equal to n, and that's pi of n. So that gives me a fairly coarse inequality on n choose k is less than n to the pi of n. So, since there are at most pi of n's in the product, as I said. So also, just by the binomial theorem, we can expand out this, and of course this is just, by the binomial theorem, it's just the sum of the binomial coefficients. And what we've just shown is that there are Well, there are n plus 1 terms in the sum, and each one of the terms is less than n to the pi of n. So that gives me that bound. And so we can now rearrange that and write n to the pi of n is bigger or equal to 2 to the n on n plus 1. Finally then, as usual, taking logarithms, I take logs to the base n, and then I change to base, then change to base e. And so I'm going to get pi of n is bigger or equal to, I take the log of this to the base n, and then change it to logs to the base e. And this expression here then, I claim is bigger than 2/3 n on log n, provided n is bigger than 220. So again, proving that this is bigger than that is just an exercise. Noting that log 2 is roughly 2/3 here helps. And again, a maple plot of this, if we have a look at a quick maple plot of this, we see why this seems to make sense. So again, I've taken the two functions and subtracted them. I did the other way around this time, and we see that it's almost exactly 200 is where the inequality changes sign. So provided we're over here, then the top function is bigger than the bottom function. And that's what I wanted to be true here. But again, you can give an analytic proof of this. This was just a graphical proof. Now, I won't go through the technical details of this, but I just want to mention here that from this, one can arrive at the following bounds on P of n, which is the nth prime. So using the above result, which I won't go through, you can show that the nth prime is bigger than 0.05 n log n and less than 3 n log n plus a half. And again, this is trying to tell us something. It's trying to tell us that this P of n looks as though asymptotically it's connected with n log n. We get an n log n there multiplied by something and an n log n there multiplied by something bigger. I won't go through the proof of it again, it's quite technical, and moreover, when we look at the result of this, if I actually put some numbers in and calculate here, we see these inequalities are actually not all that exciting because, for example, just for n is 3, which I know is quite small, it simply says that the third prime, which is 5, is somewhere between roughly 2 and 14. Well, that's not that exciting. And if I take the 10th prime, which is 29, then it's somewhere between 13 and a bit, say 14 and 84. Well, again, the bounds are not terribly explicit. So the correct order of the magnitude of P of n is n log n, in the sense that the nth prime divided by n log n goes to 1 as n goes to infinity, but this in fact is equivalent to the prime number theorem. We'll get to that later on. We have, by way, as if we needed one, we have yet another proof that 1 over p diverges because the nth prime is roughly n log n, and so I can compare this sum with this one, and we know that this sum diverges by the integral test. So these difficult but ad hoc methods really don't produce particularly satisfying results, so we need some much better techniques, and we'll develop those in some of the later chapters.